Okay, so good morning, everyone. Thank you for joining us for today's session on running and customizing your own large language models. And today, your trainer will be Kurt de Grave, colleague of mine. He's a senior researcher in AI. He has a PhD in computer science and a master in engineering science, both from KU Leuven. And he was involved in the invention of several machine learning algorithms such as neighborhood subgraph pairwise distance kernel, so NSPDK for short, or KLog as well, um, and multiple other things. So he has quite a big background in AI, and since 2015 he's a part of our organization, Flanders Make. Kurt, if you go to the next slide, I can just briefly present Flanders Make. We are one of the four strategic, you can move on to the next one as well. We are one of the four strategic research centers in Belgium, and we are mainly focusing on supporting the manufacturing industry through applied research. So we are about 850 researchers spread across a network of organizations, be it the well-known universities as well. They are all part of our network. So we are focusing on the industry, the manufacturing industry, and so that's why we are also involved in this project. So the Reboot Skills project, this is a training which is part of the Reboot Skills project, is a project from the Digital Europe program. And our goal here is to really develop a skilled talent pool of European digital experts, so you, all of you, by offering you free courses on AI, robotics, IoT, and cybersecurity. And so we mainly target SMEs and specifically employees with some background in engineering, but also unemployed people, because also the upskilling should happen for both unemployed and employed people to gradually advance together. And so these courses typically situate in awareness, discovery, up to intermediate levels of difficulty. Um, and so the main focus is not to have really expert level courses. That's where the universities come in. But we really want to give you a basis and more to get you started and to spark the interest to move on to other courses as well. So throughout this course, you'll gain a clear understanding of what LLMs are and how they operate. So including some key concepts such as tokenization, attention mechanisms, and encoding. And Kurt will also dive into prompt engineering, fine-tuning techniques, and retrieval augmented generation to show you how to adapt these models to meet your specific business needs. You'll also learn about model selection strategies, quantization methods, and how to effectively fine-tune your own LLM to enhance its performance and applicability to your data. Then what I'd like to ask you after the course is I invite you to check out also our event page on the Flanders Make website or the Reboot Skills LinkedIn page to see what other trainings we have in store for you in the coming 2 months still. So the project has been running for a year with courses, I mean, and so we are finalizing all these courses by the end of April at the latest. So take this opportunity, have a look. If you're happy about this course, also give us a shout out on LinkedIn. This is also helping us reaching out to other participants who might see benefit in getting such a course as well. So I think with this I've covered the basics. So maybe I can also give the instructions. And then I give the word to Kurt. So you'll notice all your microphones have been muted, and we can unmute for specific Q&A sessions. So whenever you have a question, do not hesitate to put it in the chat. We will keep an eye on the chat as well. And so once we've reached a Q&A session, we'll take those questions and we'll unmute the person who wants to speak or to clarify the specific question. We invite you to participate in the polls. We aim to have an interactive session as well, because it's a 3-hour webinar. It can get intense, so we want to make sure that everyone is still up to speed. So we want to check in on your knowledge. And so, as you might have noticed, this session is also recorded. So feel free to adapt your name if you don't feel comfortable having your name included in this recording. In any case, your camera is turned off by default. So, all right, without further ado, again, thank you for attending, and I'll leave the word to Kurt.
Okay, thank you, Laurent, for the introduction. First, I have to have an acknowledgement because a lot of the material used in this course is from Professor Geert-Jan Beks from the University of Hasselt and the Vlaams Supercomputer Center. And the infrastructure we will be using for the exercises is also hosted by the VSC, the Vlaams Supercomputer Center. Yeah, so what we'll be tackling, Laurent already mentioned. So we can skip that. Now, you're all here because you want to run your own LLM, right? So you're not fine with just using online websites or apps. But why is that? Why are you all here? Because it might be for different reasons. So you've seen this month in the news, for example, that DeepSeek iOS app that sends data to its host, but not just to its parent company, but surprisingly also to ByteDance servers, so the company which owns TikTok. And they even do that unencrypted for some weird reason. So one of the main motivations of using your own LLM is confidentiality. So all the data, all the interaction you do with the model, if you run your own model, you keep that information. So if you're working with confidential data, you might want to restrict the partners that you're sending all your confidential documents to. So this is to protect your intellectual property, but also to comply with the law. So you cannot just give personally identifiable information to any company around the world if they are operating from a country that does not implement the GDPR or compatible legislation. There is also technical reasons that might be for latency. So for some applications, you want low latency response. And if your request has to go over the network, then yeah, local AI can be better. It could be in some cases for cost reasons. It's not necessarily so that a local model will be cheaper, because that will really only be the case when you have quite intense use or have a very small model that you want to implement. But for example, if you have a robot that needs inference all the time, then it will be much cheaper to implement the local model that the robot can use. That goes together with the latency requirements usually. There is the aspect of robustness and autonomy. So of course, if you're using a remote API, then the API can go away at any time, or the company that you're using might cease operation. So you gain independence by owning a system that can do inference for you. Then there is the customization aspect, although you can customize third-party models as well. In many cases, with your own models, you have more control over how they are customized. So it's if you have local information, local documents, you can do retrieval augmented generation a bit more easily with local models, and you can fine-tune models to your heart's content. However, yeah, using local models, of course, will not protect you against hallucinations, the well-known phenomenon that LLMs invent answers rather than always tell the truth. So the BBC recently published a story where they did the first thorough journalistic investigation of summarization by LLMs, and they found them severely lacking in terms of telling the truth and telling the truth unbiased and unaltered. That no model does that anywhere near well enough currently to get to journalistic levels of quality. And then there's the risk of prompt injection, where if you have input from third party, be it documents in your RAG pipeline, or just as part of your prompt, for example, you have emails processed by an LLM, then there might be instructions in those documents by an adversary, because, well, you're inserting unvalidated data into the LLM. If you give the LLM powers, that is, you provide functions that it can run on your computer or your system, then the adversary might cause these functions to be called in ways that you do not want. So that is something that also running locally cannot protect you against. For a final in this introductory section is that there is a lot of controversy around LLMs still, the way they are trained. So the big suppliers or providers of LLMs use basically any training data they can get, because the more quality training data they can provide to the model during training time, the better it becomes. So they have a competitive incentive to provide more data, and they basically ignore copyright for it. It's still in legal doubt whether this is or is not legal fair use, for example. They come with a concentration of power. So if only a few parties provide state-of-the-art LLMs, that is in general not so good for society, because it gives a lot of power to the people who decide how these LLMs are trained and what kind of answers they give, because each LLM has its biases intrinsically, but also explicitly trained. For example, if you ask DeepSeek about telling anything bad about Xi Jinping, then it will refuse. Or if you ask it about Tiananmen, then it certainly will not spontaneously tell you about the massacre that happened there. But also Copilot, for example, if you ask it how to get an abortion or something, that it's quite evasive. So every model has its biases, just intrinsically, even if not explicitly trained, just from the training data itself. Okay, so what are LLMs actually? We've come a long way. LLMs were invented in 2017 when a team from Google published the transformer neural network architecture in the Attention is all you need paper, a very famous paper. So they described a pretty new combination of several existing neural network features, and also, well, actually, yeah. So the attention mechanism already existed, in fact, but this was the breakthrough of the attention mechanism. Then I guess OpenAI is quite famous. So the launch of ChatGPT has made the world aware that these models exist. And every year there appear newer and bigger models. Recently, models have become so big that they're so expensive to run that people start looking for how to make them smaller again. And so, yeah, recent releases, for example, 5.4 is a small model that is still quite good. Mistral Small 3 is also a quite good small model. We've seen releases of reasoning models like GPT-01 and DeepSeek R1, which generate output, and the output contains a reasoning process or simulates a reasoning process. And then you can get sometimes correct answers to more difficult questions than you could have gotten otherwise. Yeah, there's really been too much to discuss it all, but yeah. Okay, so what are large language models? Well, large language models are large. That's simple. So we don't call a large language model large if it has less than a billion parameters. The original transformer was only about 100 million parameters or so. Well, there were different models in their paper, but so we wouldn't call that large anymore today. The well published in the media DeepSeek v3 and R1, they have 671 billion parameters. For ChatGPT, for recent versions, it's not known how large they are. They are estimated to be around 1 trillion or maybe 2 trillion, but yeah, only insiders know. Okay, and then the training sets that are used for training these models are also quite large. So combined means that the expense of training these systems is quite large. So you need to rent millions of dollars worth of computers because otherwise you're not getting a state-of-the-art model. So tokens here is, well, we'll see that later, of course. So are about 1/3 of, about 3 characters in size. So that says something about the amount of text data that you need to train a state-of-the-art model. Okay, so what are they doing? They're autoregressive statistical models. That means that they look at a string of input and they predict the next word. So an LLM that sees once will predict output upon, and then you give upon again to the model, and then it predicts the next word, and so on. So at each point of continuation, you get a distribution of possible continuations. and they are in context. So it estimates the probability that a token should follow at location n, given all the previous locations in the document, so position 1 till n minus 1. Yeah, sorry for showing this again. Everyone has seen this a zillion times already, right? So this simple feed-forward neural network, multi-layer perceptron, technically. So a large language model is a feed-forward neural network, although it has it does use a few other functions, as we'll see in a minute. Okay, so in a multi-layer perceptron like this one, you have inputs and outputs, and in between are hidden layers. Each subsequent layer is computed from the previous one using the values of the nodes before, the neurons before, multiplied by weights. So there are a lot of weights involved. But how do we compute those? How do we determine the weights? Well, by training. And training is seeking a minimum of a function. So the minimum of a which function? A loss function. So how much does the prediction differ from the correct values that are in the training set? So each time you take a batch of input, you give it to the network, you compute the prediction, and you compare it to the true value, and then you compute backwards. So you compute how much each weight is responsible for an error in or contributes to the loss of the output. And yeah, if you have trained enough, you just stop, of course, and training is computationally expensive. So inference is easier, so you only have to go one way through the network from left to right, and you don't have to change the weights. And therefore, it's cheaper to do inference. Okay, now it gets more interesting. So this famous Attention is All You Need paper by Vaswani et al. At Neural Information Processing Systems 2017, NIPS. These days they call it NeurIPS. Maybe with Trump they'll call it NIPS again. So they combined existing IDs with some new ones. So it's defined by having embeddings, positional encodings, attention layers, and yeah, normalization. And in the end, the outputs are encoded by softmax. We'll discuss all of these in detail. So again, we predict one output token by looking at all of the input tokens and all of the previous output tokens we have already generated. Okay, so let's look at the inputs. So there are, let's say, we count T input tokens, and we have already outputted T output tokens in the stream of output. So let's say Flanders Make helps manufacturers innovate is our input sequence. How is it processed? Well, this input is tokenized. This fixed vocabulary of possible tokens is consulted, and this stream is so split into those tokens. Input vocabularies are at least tens of thousands of tokens large since the transformer paper, but these days it's hundreds of thousands. For example, DeepSeek is almost 130,000 large, its vocabulary. GPT-4o is around 200,000. But how large a vocabulary is exactly is not that critical, but you have to use the right vocabulary. So it's extremely important if you use a model that you use the associated tokenizer. Otherwise, you will get garbage. But so a string is split in tokens. It means you get a vector of integer numbers, usually byte pairs. It's also interesting to see, for example, here helps is encoded, including the space. So this is a sub-sentence tokenization, which is the common way for state-of-the-art models to work. For example, Flanders is not in the standard vocabulary of this tokenizer, but Landers is. So it needs 2 tokens to encode Flanders here. Okay, let's look at another part of the model. So we use the inputs and we make an embedding of them. So once we have selected a token that we want to present to the model, we have to tell the model which it is, and so we could have a vector of all ones, all zeros and 1 1 to tell us this is the token that is used. But that doesn't work. So that yeah, the predictions you would get from following such a representation are quite bad, because the model only has this single bit to work with. So what works much better is to give the model a dense vector, that is a vector with all non-zero numbers, and where the numbers that are given have some meaning. That is, we represent tokens in some vector space, and we want the vector of 2 related words or tokens to be close to each other, and conversely from unrelated tokens to be far from each other. So to achieve that, this tokenization is also something that is learned. But it's learned up front, perhaps. So you can use a single matrix for your embedding. The output will also be a matrix, right? So you have a matrix of T tokens, and each token requires a vector of size D for its embedding. So the representation of a sentence or a document in an LLM is hence a lot bigger than a compact representation just storing the characters of the string. So the D of the model is these days thousands large. So, well, you can build smaller models which have a few hundreds of dimensions, but usually for state-of-the-art, this is thousands long. Then a transformer looks at all previous tokens, but that in its own is not enough because their order in a sequence also contributes to the content of that sequence. So if we say George Floyd was murdered by Officer Derek Chauvin in Minneapolis, that's correct. But the same words in another order have an incorrect meaning. So clearly, we must tell the model where each token is versus each other token. We can encode that in absolute position, or we can tell the model the relative position of each token. So that's why in this model you find a positional encoding part. And the most efficient way to do that is by absolute positional encoding. That requires the least compute and works fairly well. So to each embedding of a token, there is a vector added that reflects its position in the sequence, its absolute position, right? So here the top row of this matrix would be what we add to the encoding of the first token. And the second row would be added to the encoding of the second token, and so on. So adding is quite cheap, so that saves us a lot of compute. And so the result after positional encoding is equally large from what we already had before. It's just modified. So this specific values make it so that nearby tokens have more in common than further tokens, but it depends on which encoding dimension you are looking at. Some dimensions are closely related to tokens a bit further on, and so. Anyway, so this absolute positional encoding from the original transformer paper is now, let's say, obsoleted because practically all state-of-the-art models now use rotary positional encoding or some other variant. And those are, again, a bit more computationally intensive than absolute positional, but they work better. Training works better, and so you can get better quality models by using rope. It's slightly more difficult to explain, though, so we'll skip that. But the principle remains the same, largely. Then multi-head self-attention. So what happens here is that from the embedding of a token, we compute three new vectors: a vector v for value, a vector k for key, and a vector q for query. So for each of those, we have a parameter matrix. So we multiply the embedding with the parameter matrix, and then we get v or k or q. Here, there's a multi-head concept. That is, you get better results when you split your attention among the dimensions. So the dimensions of the encoding are split into equal parts, and each part is presented to another head. That works the same, but yeah, on another part of the encoding. So the heads can look at all tokens, but what they use from previous tokens is the value part, the key part. Sorry. The result of attention is softmax of the query times the key. So we compute the product, the dot product of query and key with the key is for all possible tokens, and divided to keep things in the right order of magnitude. This vector is softmaxed, and then it's multiplied by the value. So that means that previous tokens with a key very similar to our current query, they contribute a lot because of the softmax function to what parts of value that we retain. So the result is again the same size, again the same dimensionality times the number of tokens. So say token A and B are in the same sequence, and we want to compute the attention for B from A. Then we compute the query for B, that is, we compute the weight matrix times its embedding plus some offset. And we compute the key for A, that is another weight matrix times its embedding plus some offset. And then we multiply those factors and we take the softmax for all tokens. Voila. Okay, so that's called dot product attention. Why dot product? There are different types of attention if you need very large attention windows, so context windows. So if you want to process a document that is very long, then eventually you have to figure out something else and a way to save on computation, because otherwise you have to compute a quadratic number of multiplications. Now, why multi-heading? That is, two concepts can be related in different ways. So, for example, these two countries have several different possible relations. And because of the multi-heading, so we can use those, we can learn to use those relations in different ways. Okay, so what comes after attention is a normalization. And we see here an important skip connection. So that means that our transformer is in fact a kind of residual network. So this reuses an important concept from ResNet. So the attention here only computes the residual, and the former embedding is taken also forward for better trainability of the model. Then we normalize this result, and what previously was the standard in in other neural networks was batch normalization. That's a very powerful method for whatever. So all computer vision is based on batch normalization. All convolutional neural networks use batch normalization, or at least it's very widespread. But it doesn't work very well for a transformer because our number of tokens is will change over the operation of our transformer. So we generate more tokens, and then how to take this into account for batch normalization is a bit difficult. So so Vaswani et al. They proposed, well, let's just normalize for a single token, but so only over the dimensions of this single token. And this works surprisingly well. So it turns out you don't need batch normalization for a transformer, and in fact, layer normalization works better. Okay, so this also doesn't change the width or the representational width of the model. So then we feed this information into a standard feed-forward network. Originally, this was then yeah, the activation for these neurons were ReLUs, so the blue curve. But more modern networks use smoother functions like SILU, the purple function. But otherwise, this is just a standard multi-layer perceptron network. A quite shallow one with a few thousand or width. So the hidden layer is typically quite a bit wider than the model dimension. So that's together makes the encoder. So you get an embedding, you output an improved embedding, and you do that n times. With n is variable, so it depends on your model architecture. And so this is where one of the biggest differences between different transformer implementations is how many copies of this block that you use. So you put them in sequence. But then we also have a decoder. That's the stuff that is processing the output. So yeah, it looks largely the same, except that now up front we have masked multi-head attention. That's another smart innovation of the transformer architecture. That is, we can yeah, I should go to the relevant slide first. So we can compute for a transformer in parallel all the tokens in the training set, except that, of course, tokens that come after other tokens cannot look at those previous tokens because, well, when you do inference, then you don't have those future tokens yet. You produce them one by one. So we use a mask to prevent them from being seen. So a diagonal matrix that just throws away all the information of previous tokens, of future tokens, sorry. And in this way, so you can compute the embeddings, the subsequent embeddings and transformations of all of the training sequence all at once, which makes it a lot more efficient to train than previous architectures where the network contains a recursion. There you really must follow the recursion, or well, rollout is then much more difficult. Okay, then we do, we've seen this before, right? Multi-head attention. This is then cross attention, which works essentially the same as for the input. So the only difference is that we can now look also at tokens from the input sequence. But yeah, the formulas are equivalent. And at the very end, after so many decoder steps, there is, yeah, again, a linear layer. Well, so the shortest possible multi-layer perceptron. That's not really multi-layer. So one layer of perceptrons. And then softmax. That gives us a probability score for each possible token. So the dimensionality of the output is the vocabulary of our tokenizer again. And then the tokens with the highest probability, those are the best candidates or the proposed candidates for the next part of the output. This is where also the temperature of the model comes in. So if the temperature is low, you always pick the token with the highest probability. But if the temperature is higher, then you allow the model to sometimes pick a token with a non-maximum but still high probability. So that's the way you get variation in the output given a fixed input. Okay, let's have a quiz. This is the first time I have a quiz, so I hope Nathalie will help me.
Well, so the quiz has been launched by Nathalie, and everyone can simply answer the question and press submit, and we will see the question or the results appear.
Okay, we have 14 answers. That's not everyone. Okay, let's close it. So this is false. So it requires a bit more computation, but recall that we split our embedding vector over the multiple heads. So each head has to do proportionally less work because it's all vector multiplications and matrix multiplications. So it's not actually a lot more work to have multiple attentions. So that means that all state-of-the-art models are using multi-head attention. there is a point, however, where your embedding part gets too small and you again lose accuracy in the output. So there is a sweet spot of how many heads that you can have in your model. Next question. Yeah. Okay, so that is quite clear. So state-of-the-art models all use rotary positional encoding, basically. We can go to the next question. Okay, so here most people again were correct. That is so Vashwani worked at DeepMind, which is part of Google. Unfortunately, some typos were left in the possible answers. Okay, so here also most people were paying attention. So indeed, so softmax is the method that you use to normalize the output so that it becomes a normal probability distribution. Okay, now we're getting more practical. How about we have first have a 5-minute break? Okay, let's start again. I hope everyone is back. A few of the use cases why you want to use LLMs is, of course, text generation. You can use it to summarize documents, you can use it to translate documents, or you can use it to search in document stores and retrieve information. A recent trend is towards multimodal models, that is, models that do not only accept text or cannot only produce text. So you can have image descriptions, you can these days create images. An important milestone here was the German diffusion model innovation that is now combined with transformers. So you have hybrid models of diffusion and transformer that are state of the art now in creating images and video. You can have video summarization or even generation of so far only short videos. So can I run an LLM on my laptop? And the answer is not hard and fast. It depends. So it depends on which CPU you have, especially which GPU you have, how much RAM there is, and how much RAM is on your GPU, and also which model you want to do. And what you want to do with the model, only inference, so only using the model to make predictions or to train a model. Training on a laptop, you probably don't want to do unless it's a very small model. Inference, you can do with a medium-sized model on a laptop is possible if you're a bit patient. But for real serious work on LLMs, you will want to use a GPU server and ideally a multi-GPU server or a set of servers. So how do you get hardware? Well, you can buy it, of course, but you can also rent it or borrow it or use someone else's. In general, for researchers, but also for industrial users in Flanders, there is it's very relevant that there is a supercomputer center here, and they have quite a bit AI accelerator hardware. For really big models, but yeah, I suspect that in the audience that this will be a bit too ambitious. But so there is a Euro HPC that has now clusters with up to 24,000 GPUs. But there are also just commercial cloud providers, and to avoid naming again the well-known very large ones from the US, there are also EU-based cloud providers, so where you have to guarantee that GDPR is respected, and where you don't suffer from US Cloud Act and so on. So Scaleway, Elastics, CISO, Stackit, and OVH are among the more developed players in Europe here. And then which tooling, which software libraries are you going to use? That depends again what you want to achieve. So there's a large spectrum from very basic use to very advanced use. So the very most basic users just want a GUI where they can have a chatbot, and that's provided by, for example, LM Studio. If you want a GUI with more features, where you can configure your system prompts and you can load specific models and you can have all kinds of customization, then anything LLM and open web UI are good choices. If you want to do local serving on a smaller scale, then llama.cpp is a popular library. So it's well known because it can use both GPU but also CPU inference. If your GPU doesn't have enough memory to run the model you want, you can run part of the model accelerated and the remaining part of the model slower but still functional on your CPU. Of course, the model needs to fit into the combination of VRAM and system RAM. A lot of programs or more wrappers, more front ends for this llama.cpp library. So, for example, Ollama is probably the best known command line shell around llama.cpp. But also probably the other GUI applications have this library used somewhere. Then if you have more advanced use, then you want to use a library like transformers from Hugging Face, very likely, possibly combined with LangChain at a higher level to script agency or what to do with the outputs and inputs that the model produces. But transformers is quite extensive, so it has a lot of functionality, and we will use it later during the exercises. The same holds for Ollama, by the way. If you are becoming a very sophisticated and intense user, then you probably want to use VLLM or maybe alternatively SGLang for inference, as those libraries are optimized for efficient large-scale inference in multi-GPU systems where the work is distributed and the inputs are batched for really high throughput serving. So LM Studio looks like this. So it's a simple chatbot on your desktop. You can pick from a number of open source models. Minimal tweaking is possible. But yeah, if you're using an Ollama server, then this thing cannot connect to it. That's not an option. So anything LLM can do that. So it can connect to a local Ollama server. And it can also do a lot more than the simpler GUI. So it has pipelines for RAG that we will see later. Of course, normal chat interface is there. You can pick from multiple possible vector DBs, and it can use different APIs from providers in case you do not want a local LLM. So in that case, of course, your data is uploaded to the remote server and you lose confidentiality. So more sophisticated users will want access to a command line or API. Then the most straightforward choice is Ollama, very popular. So in Ollama, you can use any of the popular open weight models like Llama 3.2 from Meta, 5.4 from Microsoft, Mistral models, Gemma from Google, and so on. Now the install script is a bit headstrong, so it's best if you install it to do that inside a container or a VM. So how does it work? So you can start a server with or without ampersand at the end, depending. So the ampersand runs it in the background, and without the ampersand, you get the output and more the log of the server, but then your shell is occupied. So in the exercises, either you run it without ampersand to see the output, or but then you have to run a separate login shell to the VM to do other stuff. And then once the server is started, you can run a model. And if you run a model that is not yet in its collection, then it will download this model. For example, Olama Run Llama 3.2 will pull the model from the repository, unpack it, and give it to your GPU as much as possible. And you can then type a query. So this these three signs are a prompt or an indication that you can type a prompt. Okay, then you can query it to about which models are installed. You can pull new models without immediately running them, and you can show information and details about the specific installed model. Removing the models again is just with the RM prefixed or prepended with Olama. So that's relevant because models, of course, are large. So every even smallish models or gigabytes large. So you certainly don't want to keep them if you're not using them. You can have a list of all active models, and you can stop running a specific model. So this is an example of real output. And so if you ask it to show details about DeepSeek R1, if you have that installed, then it will tell you this information. And what this also shows you is that you're not using actually DeepSeek R1 in this case, but we are using a much smaller distillate of DeepSeek R1, which, by the way, doesn't have nearly the same quality as the full-scale model. So this is a distillate of Qwen2 with nearly 8 billion parameters. It has a context length of about 130,000 tokens, so you can have prompt input of up to that length, and if the prompt is longer, then it cannot be, or the first part drops out, right? So it can only take that much tokens into account. The embedding length of the model, so the model dimension, is 3,500. So that's the D parameter that we've been seeing in the previous part of the session. That's the width of the vector. The quantization of this model, this particular installed model instance, is 4-bit quantized using the K and method in Llama CPP and at medium size. And then it tells you a bit about which kind of roles there are in the model and which specific delineation tokens there are, and the license, which MIT license is a very permissible license, so you can do anything, basically anything with the model. Okay, then models come with a size, so you have the number of parameters. If you download them in Olama, the download size will typically be about half the number of parameters, in that most models are quantized at 4 bits per parameter. But then there is memory size, and that is again a bit larger than the download size, because the model has to keep track of all the representations of the previous tokens in a sequence, and that also takes memory. Otherwise, you cannot compute the next token. So that's why the required memory is a bit higher. But yeah, you do need that much memory on your device. So again, in Ollama, in all other systems that use Llama CPP under the hood, you have to have at least that much memory in your GPU plus in your host system, so in the computer itself. And of course, you need some memory left for your other programs on the system. Okay, so then chatting with a model can look like this. So you run Ollama, run a specific model at a specific size. So this is the 1 billion parameter version of Llama 3.2. And then you can type, when you get 3 times the bigger than sign, you can type prompt, and then you get an answer from model. You can ask more questions, and then you say /by when you're done. You can run a multimodal model, and that's there you can provide an image as input as well, not just text, and you can ask questions about the image. So sometimes these multimodal models are right on track. So yeah, ChatGPT 4.0 can of course do the same. However, when you ask such an open weight model that of smaller size to about formulas, then they're sometimes totally wrong, or often totally wrong. So this model is not trained well enough, and isn't large enough to answer this question correctly. So you get total garbage out. Whereas, state-of-the-art models like GPT-4o can correctly interpret such an image, and tell you the interesting things about it. Ollama also gives you the option to have a very small file, a model file, it's called, where you can describe a configuration of a model and customize it the way it works. So you say you start from a base model, in this case standard Llama 3.2, and you choose a temperature. So recall, temperature is higher temperatures means that the model is more likely to use the non-maximum predicted token, so you get more variation in its output. Some say the model gets more creative. And you can set a system prompt, so a prompt that is prepended to your normal prompts. So this can make the model behave quite a bit different than its standard operation. So if you have a file like the above, so that's just a few lines of text, you can say Ollama create a model name and then the file, the model file. And then when you chat this model, so we told it to be a paranoid robot, then it will act like a paranoid robot. So this works quite well. For prompt engineering, so the art of writing the optimal prompts, there are a few general tips to be aware of. So if you're specific, so you provide as many details about your question as you have to the model, then you generally get a better answer rather than very brief questions. some researchers found quite funnily that being polite to an AI model helps in the quality of answers that you get. So this is a bit weird. Why would you be polite to a computer? Well, the reason is that the training data set contains unpolite texts and polite texts, and usually in forums and papers where people are polite, they are generally more correct and more accurate in what they are saying. And so if you are polite to the model, then you get more influence from the training sets where people are accurate, and so you get a more accurate answer. Then you can against any model these days, you can, if you ask, are you sure, you will get a completely different answer than the one it just gave you. Because instruction models are trained to to make this assumption that if you ask them, are you sure, they will assume that we were totally wrong. But so you can do iterations or if you ask more queries about what it answered, then you have, sometimes you can nudge it to get a correct answer where first you did not. It always helps if you have examples of question answer of the type you want an answer to. If you provide those in your prompt, then chances are that it will be able to answer your new question better. You can boost that to a higher level by including relevant documents that provide context into the prompt before or after you ask a question. And this has been institutionalized by RAG, so retrieval augmented generation, that we'll see in a minute. And you can ask for chain of thought. That is, if you just say to a model, think step by step after your query, then the model will list out all the steps required to get to an answer. And then the chance that it will arrive at the for a difficult question to the correct answer is higher. And this principle is institutionalized now by reasoning models such as GPT-o1 and DeepSeek R1, the famous release this January. And slightly more recently, Stanford S1, who demonstrated that you can get to this chain of thought reasoning models quite efficiently. Okay, so this RAG that I mentioned already a few times, what is this exactly? So in general, you have an LLM is pre-trained with the entire internet, if you can. So a very large data set. But then you usually also have specific documents that are not public or not on the internet. Or just you want the model to pay more attention to specific sets of documents, even if they are on the internet, because you know that they are relevant to your question. So then the trick is how to get these documents into the model, or how to make the model take those into account when answering your question. That's what RAG is for. So first you have to have those documents ingested. They need to be read by your code. You compute embeddings for your data. You have a query for the model, and then the relevant parts of the data are added to your query. So a good library, one of the standard libraries to do this is Llama Index. And we'll use those in the exercise session at the end of the course. So you have a number of readers. Simple directory reader will read text files in a directory, but you can get much more sophisticated models or specific models for specific types of input. Sorry. You can create documents on the fly, but so there are all kinds of possibilities for ingestion, all prefabbed. And then you need an index. So a data structure that contains the documents you want to query, or that can possibly be used by your query. And the standard way to do that is a vector database that is, typically the document is split into chunks, and each chunk is treated separately. And you compute an embedding for each chunk. In Llama Index, by the way, chunks are called nodes for some reason. You can have a summary index that then computes an overall embedding, or you can have a knowledge graph constructed where you use similarity between documents or chunks to compute a graph. So the graph is then a sort of a discretized nearness or proximity of those vectors. So what we saw before, so word or token embeddings. So one hot encoding is not good. A dense embedding is good, and to get a good dense embedding, you need training. And a good, again, so semantically close tokens should be close to each other in this high-dimensional vector space. So for chunking, this is a hyperparameter typically. So you have a fairly short token sequence of a few hundred tokens typically, but yeah, this really depends on the application a bit, what is appropriate. If it's too small, yeah, then you have too little context to answer a query, then it won't help. If it's too large, then you will increase your prompt size very much, and yeah, so also make it more difficult for the LLM to find the relevant piece within the chunk. So these are important hyperparameters of your RAG system. So you can set up a simple RAG with just a few lines of code using Llama Index. So you ingest some documents from a directory. You select an embedding model. The choice of which embedding model you pick is quite important in the quality of the results that you will get. You get more computational effort with a bigger embedding model again, but it's usually worth it. You create an index, for example, with the standard vector store index, or in another specialized vector database. So how do you answer a query? So you compute the query text input by the user is you compute an embedding over that, and then you compute you search in the vector database for the k nearest chunks. This search is almost always done approximate, and because these vectors are large and you have many chunks, so finding the k nearest neighbors to the query is, if you want an exact answer, the exact k nearest vectors, that's fairly expensive because you have to have a dot product with all the vectors in the database, just to be sure. There are a few ways you can accelerate that, but if you really want the exact answer, yeah, there is only so much you can do. If you're okay, and usually that is the case, with an approximate answer, then there are much faster methods to compute this similarity. And so you found those top k or approximate top k, and you put them in the prompt along with the user query. And then the LLM will synthesize an answer from the assembled chunks. So you do retrieval to augment the generation. Retrieval, augmented generation. RAG. Okay, so querying works like this. So you pick a specific LLM model. Yeah, again, bigger models will give higher quality output. Then yeah, you select a query engine. So as I said, the specific query engine will have a balance between accuracy and finding the nearest neighbor set and speed. And then you run the query like this. Okay, so there are specialized vector databases that store documents and their embedding. Chroma is well-known, Weaviate, Milvus are the well-known specific vector databases. You can also upgrade the standard SQL database, advanced SQL database like PostgreSQL with an add-on, a PG vector add-on, where you have also vector database functionality, but then combined with all the benefits that you get from a standard SQL database. So it has full ACID compliance, but it might not be the fastest vector database when you look at it purely as a vector database. It's a very active field of research, so there are new papers all the time about new approximate nearest neighbor algorithms. For example, ISAC disk ANN is a method where you can have a huge vector database that has only very little constant memory use, RAM use, and all of the database, and also even all of the indexes are only stored on SSD storage. So this becomes interesting when you really have multi-terabytes of documents stored that you want to use in your local rack system. Okay, now quantization. That's quite important if you want to run local LLMs. Why is that? Well, that was already realized a long time ago. So these numbers are from more than 10 years ago. It was on 45 nanometer chips back in the time, but the principle stays the same. So if you do multiplication, which our LLM is doing in huge amounts. If you do multiplication of two numbers of 32 bits, that consumes a certain amount of energy. But if you only have to do a multiplication of lower bit numbers, so less accurate and lower range numbers, then you need to flip a lot fewer transistors. You have to drive a lot fewer wires. And so the energy used is a lot lower. It's super linearly lower. Same or similar thing holds for required bandwidth and, of course, equivalently required memory for your numbers. Those are proportionately lower when the number of bits in your number representation gets lower. So because of our LLM has to do many billions of multiplications of numbers, the relative cost of each multiplication is becoming very relevant. And so, yeah, this is if the smaller representation numbers are anywhere near the same quality or anywhere near as usable as the large ones, then it's clear that it's better to use the smaller ones. When you look at hardware to do inference or training, then memory bandwidth is often the main limiting factor. Because LLMs need to use so many parameters. All of these key and value and query matrices need to be stored somewhere. And all of these embeddings of previous tokens need to be stored somewhere, and they need to get to the compute in order to be used. So memory bandwidth is, as I said, often the limiting factor. And this is sort of a best case of how much bandwidth you can get on a device. So if you have on-chip memory, so SRAM memory, then you get a very large amount of bandwidth. So if you can have your data there, then you're set. Then there is something like that's called high bandwidth memory, which is basically DRAM memory with a lot of pins that are mounted very close to the compute chip. And those get up to about 8 terabyte per second in a GPU. And B100 has 8 terabyte per second, and MI 350 325X has 6 terabyte per second. So those two are, I think the highest achieved numbers so far. Then a consumer graphics card that comes with GDDR memory can have up to 1.7 terabyte per second bandwidth. So that's for a top-end NVIDIA card. A server, a normal CPU server, so the best ones of those come with 12 channels of memory per CPU, and that gives you half a terabyte per second approximately. And then, if you need to store it to disk, well, rather flash. So an SSD, then, the best SSDs are approximately 15 gigabytes per second. So that's quite a bit lower. So that was on log scale. So if you plot the same things in linear scale, then yeah, there is a striking difference in height. But how about typical systems? Here, the best GPU for consumers is again listed 5090, that's just released, and the best server CPU, the Epic, and next to them here I plot what is more a typical computer, right? So if you buy, you go to Dell. Your country and you buy a Latitude, what do you get then? That's quite a bit lower bandwidth than for a typical system than the best server chip, of course, because it only has 2 channels. And if you buy a mid-range or a low-end GPU, you also get a lot less bandwidth than a top-end GPU of 2,000 euros. And many hundreds of watts, 600 watts of power. Okay, so now we know that the representation of numbers is quite important. Until LLMs, neural networks were always trained in 32-bit floating point. Now that is no longer the case, so we often don't have 32-bit floating point numbers anymore at all because they're not used during training. LLMs are partly trained in 16-bit, but these days often also in 8-bit FP. But quantization is in general the principle of using a lower precision representation of your previously higher precision numbers. So starting from 32-bit, you can go to 16 bits or 16-bit brain floating point, which spends more bits towards the exponent and less towards the mantissa. So it has a larger range, but a lower precision within its range. You can go down to integers, which are more easy to compute with 8-bit, 4-bit, and even lower bits are used. And there are even binary LLMs around these days. So it decreases your memory requirements. It's more efficient in computation, and it decreases power consumption as long as your hardware has good support for this numeric format. If it doesn't have support, then it will not be more efficient. Sometimes it can still decrease your memory requirements, so it can still be a valid choice. Okay, but however, if you do quantization, you will lose accuracy. So the model will not give answers that are as good as the unquantized model. So how do these number representations look like? These are examples from NVIDIA. How you can have a number that is close to 0.4 in half precision, so FP16, you have always a sign bit if you want to be able to represent negative numbers. That is a bit that you cannot lose. You have an exponent to tell us the order of magnitude, and you have a mantissa to have some precision in where around that order of magnitude exactly your number is. As I said in brain floating point, there you have more exponent bits and less mantissa bits. Oh, that was too quick. And then FP8 only has 8 bits, and there are two different 8-bit floating point formats around. So E4 M3 and E5 M2. That has the former has a smaller exponent and the latter a bigger exponent. And so in LLMs, these are both used. So for forward, for inference, you typically use the former. And for training during backpropagation, you need more range. So you have to use the latter, or it's better often to use the latter. Okay, so if you can also do representation with integers, but then you want to scale them at the time of use, usually. So you have a scaling factor S and an offset Z. And you have to store those, because if you want to use the actual number, that's then you need to retrieve those. So the trick is to have lots of numbers, a chunk of your vector, and to isolate the most suitable scaling factor and 0 points for those on average. And then you can represent such a chunk. But if there are outliers in the chunk that you're looking at, this will, of course, negatively influence the quality of the model, because you have a less good representation of your weights. So typically blocks that the size of blocks is always a power of 2, like always in computers, but 256 seems to be a popular block size these days for strong quantization. There is such a thing as normalized 4-bit floating point representation, or NF4, where so the distribution of your weights is normalized, and then the location in this normalized distribution is stored as a 4-bit number or lower bit number in the weight vector. This quantization can occur after training, where you just train a model in whatever format you prefer, and then afterwards convert the weights, either by just looking at the weights themselves, or also using some data. The alternative is to already prepare during training your quantization. And there are these days constantly new methods of quantization come around, pop up, and so this is hard to follow, but that's also why I don't discuss in a lot of detail the different methods, because next week there will be different ones, but the principle remains the same. So this is quantization aware training. So you change the way you train the model. So training becomes a bit more expensive this way, because you do more work. And also you have to know the quantization level that you want to achieve after training, because this influences your training. So you do the quantization during inference. So the forward pass here in this diagram, it's the downwards direction, and then during backpropagation to backpropagate the loss, then you skip the quantization. And so this way you get a correct backpropagation or a more suitable backpropagation of the loss in a way that takes into account this quantization. So this generally produces better quantized models, again, with the gotchas that I already mentioned. There is code in Llama CPP to quantize included. And then you store the model in GGUF, GPT-generated unified format. That's a recently introduced format for quantized models. And there are many variants to pick from. So depending on the size of the memory of the device you want to run the inference on, you can pick a different method or a different implementation of a method. And these method names, Q and then the number, so the number stands for the number of bits used for the least accurate numbers in the quantization. So you also need to store offset and scaling factors. So the average numbers of bits per parameter is always a bit higher than this integer, but it can be somewhat close. Okay.
Good. Sorry to interrupt. Before you move on, just wanted to just mention, so it's 11 o'clock, regarding timekeeping, that you just keep it in mind for the exercises that you also plan to give. So just a heads up. All right, perfect.
Okay.
Thank you.
Okay, I need to go faster. I get. Okay, can do. So Llama quantize is a comment that can do that. Okay, this is an example run. So you convert one GGUF to another, and you specify the quantization method, and you have a previous size and next size. It takes quite a while. So in this case, you compress the models fourfold, but it takes quite some time. So we won't do that for our exercise, but so this is how it would look like. You want to have some idea of how accurate the model is, especially if you're gonna reduce the accuracy by quantization. And the standard method to estimate that is perplexity. So that is more or less the surprise of the model, how surprising some validation set is to the model. So you let the model predict the next tokens for some validation data set. And if the prediction of the model matches the actual value in the gold truth data, then the distribution matches, then you have low perplexity. lower is better. But yeah, so you need a data set to compute this. And so there's a tool to do that computation. So you have some database you measure this on, in this case, Wikipedia extract. Okay, and then with a quantized model, you get different results. And so in this case, it's 4 times smaller. So you get 4 times lower load time. And the perplexity, though, is 22% higher. So it's clearly a worse model. So you will have lower fun of talking to it. But you can fit it in 4 times lower memory. And it also operates a lot faster. So you can produce more tokens per second. Okay, and there is a separate tool for benchmarking it. So it scans the grid of different hyperparameters, such as how large is your prompt, how many prompts do you process in parallel, so the batch size, the output size, and then it can create a table like this with different measurements. Then a bit different topic, but still something important, I think, that should be mentioned. So you heard me talk before about distillation and about distilled models. Now, what is that? Well, you have a training data set. You can use it to train a big model, or you can use it to train a small model. Now, the optimal way to train a small model is actually to first train a big model, to have that big model make predictions, and to use the distribution of so its output probabilities to tell the student this is how the answer should look like. And this gives more information to the student than just the gold truth labels in the original data. Because the gold truth labels, or in the case of LLMs, the training text is only one possible reality. So a text could be continued in different ways. And a very big, powerful teacher LLM is actually a very close representation of the different continuation probabilities of this text. So the student can learn a lot by looking at the output distribution of the teacher. And so this way you can make small models that are still very high quality. So this is distillation. So if you heard about a distilled model, this is the way it's trained. Okay, fine-tuning, last topic. So if you have a standard model, you can specialize it to perform a specific task, a specific summarization, recognizing specific terms in a text. So you have a task you want to be done, and just prompting is not good enough. So if you ask the model, I want to do this with this text, it doesn't perform well enough or reliably enough. So you can have some training data, and then you can do domain-specific specialization of the model. Now, if you just train on your data, on your fine-tuning data, there is some risk involved, like there can be a reduction of alignment, and you can also have catastrophic forgetting, so that the model doesn't know what it's trained on before you came along with a tuning set. It's also expensive, so a very large model training is you need to do very many iterations of inference through the model, and each iteration is at least twice as expensive as just inference, because you have to do the backpropagation. Model also needs is large. You have gigabytes of weights, and if you need separate weights for each problem that you want to solve, then your storage requirements go up quite quickly. Your training time is high, and you have a problem of forgetting. And then if you want to load a new model for every new problem that you come along, then you also have the extra latency of loading those model parameters into your system at the moment when you encounter the problem. That's also a problem for some applications, at least. And so the solution for this is parameter efficient fine-tuning. And that uses adapters, LoRa and or QLoRa. What is that? Well, an adapter is a shallow multilayer perceptron that is inserted into the layers of the model at specific places. And these convert what the layers above see from the input. So they change what the model sees, so they change the behavior in that way. Notice that these adapters are always inserted inside a residual connection. So there is a skip connection around them. And what you train is only the adapter for fine-tuning, and the rest of the weights are frozen. So the original ones are not modified. You can still do one better. That is, we can have low order rank adaptation. That is an adapter where you don't have a full matrix, but you have a factorized representation, where each factor is less than half as large as the original. And so this further reduces the number of weights that you must store. So that's, yeah, of course, a low rank approximation, because the rank cannot be bigger than the width of the two factors. And yeah, so you train those factors, and again, you freeze the original weights. And you can do that on a factorized, on a quantized model, where, yeah, again, you do blockwise quantization, because then an outlier will only influence one block. You can do two levels of quantization, where you quantize your scale factors and your offsets. And then you dequantize as you pass by a layer, just in time, which reduces memory use again. we reached the quiz. So just this quiz, and then we'll get to the exercises.
Sorry, I see that the poll order and the slide order do not match. Sorry.
Yeah. Okay. Well. Yeah. Then I'll not advance the slides until we come to the proper question.
I've launched the correct question.
Okay. Okay. That's also an option here. Okay, let's see until people have answered the question. I'm happy to see that most people do remember what we told. Yeah, I guess we can advance a question. Okay. So the correct answer here, of course, was VLLM for that's the highest performance inference library. Then the question, what is an embedding? We've seen this many times, so surely everyone will know this. No pressure. So the certificate you get does not depend on the answering of questions. Yeah. So I'm happy to see that just like an LLM would do, the distribution of answers here is quite nice. So there is one correct answer, and there is one answer that is very nearly correct in that indeed, yeah, you can use it as a sort of compression method, but of course it's a lossy compression. But so the fourth incorrect answer is not entirely incorrect. So congratulations, that's well answered. Then next question. That should be easy as well. Okay, so yeah, of course, lower bit representations are faster. And this is something that everyone remembers. So indeed, distillation is a technique used to transfer knowledge from a large pre-trained model to a smaller model, a student model. Okay, LoRa is a low rank approximation. So that these were that was the last slide. So where the factorized matrix of where factors of low rank are used to approximate the full matrix. And then the last question. Oh, that was a bit too quick. But yeah, okay, it's not that important. So you recognize a number of actual European cloud providers here. Sorry, I gave the answer away too quickly. Okay, so there is a feedback form, but first we have the exercises. But let's move on to conclusions. So it's running a small language model locally is easy. As long as you have enough memory, you will be just fine. Wrong direction. So quantization helps if the original model is too large to fit in your memory. If you have done the exercises, you have seen that open weight models, even fairly small models, are pretty good already out of the box. And you can specialize them by custom prompting. As we've seen in the slides, you can have system prompts, for example, that change the behavior of your model. You can have retrieval augmented generation, where you take a document store and retrieve relevant snippets or chunks and insert them into your prompt. You can have fine-tuning, as we've seen with LoRa's, that's become quite efficient, and hopefully several people have managed to train the fine-tuned model on the pandas dataset. And you can have distillation, which is what is used these days to do very efficient fine-tuning from bigger models. So that concludes this course. So thank you all for your attendance and your feedback. And yeah, there will be more courses from Reboot Skills, I think. I'm not organizing those. I'm only involved in this one. So I hope you see you around sometime later.
Yes, thank you so much, Kurt, for the conclusions. I've also shared the feedback form link in the chat. Thank you for filling it out. We really need to report back about every single one of the courses. We will send you an email with the certificates, and we'll include the link again to Reboot Skills courses. We still have a few more coming up the next couple of weeks. A few online, a few in either our Leuven or Kortrijk office, so feel free to check those out. And thank you so much, everyone, for attending.